Good morning, good evening, good afternoon, wherever you may be in the world, whether you're watching this live or whether you're watching it later on the recording. Welcome to the third lecture in the series of 4. And I thought, as I promised on the first day, we start today off a little bit different with a demonstration from my friend that I've known since I was 11 years old, Dr. Simon Fricker, and he put together a little video demonstrating one of my other passions when I was a kid, which was chemistry. And I want to show you a little video of him demonstrating the Thermite reaction, which is the reaction between aluminium powder and iron oxide powder. Let's go over and watch that now.
Hello there, this is Dr. Simon Fricker with another chemistry demonstration. This is a thermite reaction between iron oxide and aluminium to produce molten iron. I've also put a pan of water underneath so that when the molten iron drops through, a secondary explosion takes place as the water is split into hydrogen and oxygen and then recombines again to form water.
Ready?
Considering the chain of events in this demonstration, if you think back to the awful atrocity that happened in New York, you had a situation with the fuselage of a plane embedded in the top of the building, mostly aluminium, lots of heat, probably lots of molten metal, iron and aluminium, and of course there would have been water sprinklers in operation.
Wow, thanks Simon. What must the neighbours think living next to you? That was brilliant. Brings back lots of childhood memories. So today what I want to talk about is, following on from what we were looking at yesterday, where we looked at the idea of induction and using two coils in a transformer. And as we said, what we put a AC current in this side, we'll get an AC current out the other side through induction, even though there's no electrical connection. But the thing with this is that these are non-resonant. So no matter what frequency we put in here, we get the same frequency out the other side. So with mains, we put 50 hertz in the UK, 60 hertz in the US, and we get an AC current out the other side. But what do we can now start to move towards is if we take a coil like that, and then we put in what's called parallel with that coil a capacitor or what's called a condenser, then this is a tuned circuit. And it will resonate at a specific frequency. If we make this what's called a variable capacitor or a variable condenser, then we can actually change the resonant frequency that tuned circuit resonates at. So if we got a tuned circuit here, and we could set them to the same frequency, then we'd get a resonance between the two things. And this is what we've got with radio. So then what we can do is actually feed into here information, which will then be converted into a particular frequency, which will, through the waves, come to this other side, and out will come the information here. And if those are very, very close together, so this would be called the transmitter. And this would be the receiver. And if they were in pretty close proximity with each other, then we would get the information that we put in here would come out the other side. If we wanted to be able to have these further apart, then we're going to need to have some kind of aerial or some kind of antenna, which is what I'm going to talk about tomorrow. But essentially what we would do on each of these tuned circuits is we would ground or earth one side of it, and we'd stick an antenna on the other side of it. And that's what created the early radio. And depending upon the power that you put in, which we talked about yesterday, and the distance between the two and the effectiveness of the antenna, literally these two tuned circuits could be thousands of miles away from each other. And that's how radio works. But then we've got to go, how do we actually put information into this wave? Yeah, because what we've got is just a wave there. Yeah, how do we actually put information into that wave? Well, in the first instance, when they were starting to work with radio, how we conveyed information was very simple, because what they did was they just interrupted the wave. Literally, they switched it on and off, and they used something that already existed, which was called Morse Code. And what they did was they switched the wave on and off, and it could be on in like either what's called DITs, small time, or DARs. Yeah, and you may even know, from Morse Code, if ever you were a Cub Scout or whatever when you're a kid, diddy-dit, da diddy-dit is SOS, save our souls. And literally what they would do is they would switch the transmitter on and off, and then what would happen on the other side is that they would receive that here. Yep. So did da diddy would come out the other side for the radio operator to hear the particular distress signal. And that way of conveying information was called CW, or what's called continuous wave. But it's very slow, so you can't convey that much information very quickly. So then the next way of encoding information into the wave was by changing the amplitude of the wave. So for instance, for voice or music, then the variation in the voice, the variation in the music would change the amplitude of the wave. And what we can then do is decode that at the other end by putting a diode in the circuit, and then literally we could put a pair of headphones here, and with no power, no battery, no amplifier, we can actually hear the radio broadcast. And I used to make lots and lots of crystal sets when I was a kid, experimenting with these things. Now that was called AM, or amplitude modulation. Now we can convey information more quickly than CW, in that we could actually convey the voice or convey music. And this is what created AM radio, which was or medium wave radio. But it was pretty low quality. And to be able to increase the quality, we need to be able to send more information in the wave. So what we need is if we want to be able to convey more information more quickly, then we have to be able to increase the bandwidth that we've got. Now, the bandwidth is the difference, the amount of frequencies that a particular wave or signal would convey. So, for instance, if we were to look at AM radio, that used to have something like a bandwidth of 9 kilohertz. Well, if there's a bandwidth of 9 kilohertz, then that's how much information we can convey. It's a fairly narrow bandwidth, which is why it was pretty poor quality. But that was a limitation to amplitude modulation. So what they then invented was something called FM, which is frequency modulation. Which created FM radio. Yep. Now, the bandwidth of a FM radio station is significantly bigger than the bandwidth for a AM radio station, which means that we can convey more information, which means therefore we've got higher quality of music, higher quality of sound, which is, FM radio was really created to be able to broadcast what might be called high fidelity or high quality music. But even that then started to have some limitations. Frequency modulation, basically, where amplitude modulation is where we change the height or the depth of the wave. Frequency modulation is where we actually alter the frequency and we encode the information in the variation of the frequency. But that's also had limitations. This is all how this is developed. But again, to get the increased bandwidth, we had to go to increased frequency. Yeah. So, AM was around 200 to 1600 for long waves, medium waves. Short wave broadcasts would be up to something like 30 megahertz. But then we start to get into what's called VHF, very high frequency. So now we can increase the bandwidth, and because the frequency's increased. So the FM broadcast band, for instance, in the UK, was around about 88 to 108 megahertz. There was 20 megahertz to play with, whereas the entire shortwave band was only 30 megahertz. Yeah. So what we've got now is we've got more bandwidth to play with, and the radio stations would take more of that space, which means we can put more information into the wave and therefore increase the quality if you look at it from a music point of view. But then what came into play is digital, where we digitize the information into ones and zeros, and we put that information of ones and zeros into the wave. But depending upon the amount of that information you want to convey depends on the bandwidth again. So to get digital, we needed to increase the bandwidth even further, which means that what we've got to do is use a different frequency band. And this is what we're seeing now. Now that we've got mobile phones, and now those mobile phones can pick up Wi-Fi, then the Wi-Fi in your home at the moment works at between 2.4 gigahertz or 5 gigahertz, which means we can have a significantly bigger bandwidth, which means we can get, or what it's like is bandwidth is like the size of the pipe, if you like. Yeah, and the bigger the pipe, the bigger the bandwidth, the more information we can get through there in the same amount of time. And as the data rates have been increasing, now we're looking at things like 50 to 100 megabits per second in our home Wi-Fi, then we need a significantly bigger pipe to get that number of bits down the pipe every second. And now 100 megabits is not considered to be that fast. We're now talking about gigabits per second. So if we want to be able to digitize and pass like gigabits of information down, and a gigabit is 1,000 megabits, yeah. So 1,000 million bits per second, we need a bigger pipe, we need a bigger bandwidth. And to be able to make the space for that bandwidth, we need to increase the frequency, which is why now we're looking at using frequencies of up to something like 50 to 60 gigahertz to be able to transmit that amount of information from one place to the other. But essentially, it all works through this process here. This is how, you've got the mast, the transmitter for your mobile phone, and then you've got a receiver in your mobile phone which picks up the information and then converts it into either sound or a web page or anything like that. That's how this whole thing takes place and how it's advanced over the last probably nearly 200 years, something like that. Okay, so tomorrow what we're going to look at is, for this to work effectively, then unless these are very, very close together, we're going to need some kind of antenna or some kind of aerial. So what I'm going to teach you about tomorrow is about how aerials work. And this all comes into correspondence, into vibration, and into resonance. Okay, I shall see you tomorrow, 11 o'clock UTC, GMT, or 1100 Zulu. Have a great day.